Okay, thank you. The next speaker is Ryan from Arm. Ryan, please start whenever you're ready.
Okay, thank you. Yes, hello everyone. My name is Ryan Hulguin. Hope everyone had a really good lunch. Yeah, I'm an application engineer with Arm. I've been doing ATPESC for the past several years now, and hopefully today you'll come away with some knowledge on how to use our tools, and hopefully you feel real comfortable using them. We like to think that our products are pretty user friendly. A lot of information can really be gleaned just by moving your mouse over things, but yeah, I'll be able to demonstrate that later in the talk. So, so for the agenda, I'll start off with just some general debugging and profiling advice, and then move over into ARM specific software solutions, in particular debugging with DDT and then profiling with MAP. And at the end, just for reference, I'll list off some data specific settings that you guys need to be aware of if you want to participate with the hands-on or go through the examples that I've got provided. So first off, debugging. So debugging is really the art of transforming a broken program into a working one. I have a little mnemonic device here called Traffic to help you think of ideas of how you would solve your problem. But the real takeaway from this slide is if you encounter a problem, I mean, it doesn't even have to be code, but in this case, we're talking about there's a problem in your code, and you want to be able to break it down into as small a piece as possible that you can tackle. And when you do so, you want to be able to, if at all possible, be able to reproduce it so that if you ever come across this problem again, you can actually learn from the problem. So you don't have to keep fixing the same bug as it pops up multiple times. And you can do this a variety of ways. You know, Jay, you already talked about, using print statements in your code just to get information. And while that will give you information that you're looking for, sometimes that may not be the most efficient one, or it may not be a solution that you could use, especially if you run into a problem where it only shows up when you run thousands or hundreds of thousands of processors. You can try and put print statements there, but being able to just dig through all that information is going to be quite a challenge. So that's where tools comes in. And on the other side of the coin, once you fix your code, usually a lot of people think that that's it, right? It's fixed. Let's move on to the next thing. But there's also performance to be gained if you actually take the time to profile your code and figure out where time is being spent in the code and try to identify hotspots. So in this diagram, it's not trying to say that file IO is like the greatest thing that you should concentrate your efforts on. What this slide is really saying is that if you have a file IO bottleneck, it's going to have a more severe impact on performance than if you had, say, a memory bottleneck. Because if you're having to read or write from a slow disk, there's not much you can do about that until you fix that bottleneck. And these are things that you can just focus on just as a general rule when you're profiling the code. And this can be, like I said, analogous to print statements in debugging. You can also put in your own timers in here. So if you want, you have to put in the work to figure out where time is being spent. But fortunately for us, ARM has created a tool that can just insert these timings for you, so you don't have to bother inserting that into your code. So if you've got like a working application, and you want to be able to improve its performance, you really want to start with a realistic test case, something that you plan to run on every day. And then you would profile your code, like I said, either with tools or inserting your own timings. And then you want to look for the significant, try to figure out, where the time is being spent. Ask yourself, is there a problem that I see that I wasn't expecting? Maybe it's taking too long to write data to a disk. And so those are the kinds of things that if you don't think about and you don't ask those questions, you never know just how much of an impact it has on your code until you actually profile it. And if you do come across those types of problems, you want to try to think about ways that you can solve it and make the code a little bit better. So Arm's solution to this is a product that we call Arm Forge. I know you all have access today to Theta, which is fantastic. But if in the future you were going to move on to a different site or go into the workplace, and chances are that if it's on a large HPC machine, it has our tools installed already. Mainly because it's a fully scalable. Like our code runs on something as small as like one. You can run it on serial code, or you can run it up to hundreds of thousands of cores. I mean, just recently we ran a full, almost the full machine of Theta for a debugging session, and it's very user friendly. Like I was saying, you just move your mouse to try to figure out more information about the state of the variables and so on and so forth, which I can show in the demonstrations. So DDT, so Forge consists of both DDT and map, where DDT is the debugger. And there are two ways that you can run it. You can either run it interactively with the GUI, which you see on the right here. And depending on the number of MPI ranks, if it's a small number, you can easily switch your focus between the ranks just by clicking on the boxes. What you see here, we have 8 MPI ranks going from 0 to 7, and they're all in the pause state because they're all red. If it was green, that means they're all running. And that's pretty useful if you're able to get a job right away in the queue. Sometimes, the queue might be backed up such that it's hard for you to predict when your job is going to launch, and you still need to debug your code. So we offer another way of running DDT, and that's called offline mode, where you just stick DDT -- offline in front of your MPI launcher command. And at the end, what it's going to do is it's going to produce this nice little HTML output that'll show you what things are happening as your code runs. And if there is a crash in the code, it will also run until the code crashes, and it will give you a nice little snapshot of what the values are of the variables right before the crash occurs. So it's kind of like having a photo of the crime scene just as a crime is occurring, right? So you can investigate, what happened if your code crashed using offline mode. And the other side of the coin, we have our source code profiler, where you not only get like general information about how your code is progressing through time as you move from left to right, so that this is when your code starts, and then at the right is when your code finishes. And based on the color scheme, you can determine what your code is doing. So in here, we can see that green stands for some type of calculation, and then blue stands for some type of communication. So for this code, you can see that it's mostly doing a lot of calculation with just a little bit of communication sprinkled in as the code runs from left to right. And you can quickly see at a glance, if you're looking at the memory metrics, you can see just how much memory is being used by your program from start to finish. You can see that as we move into this section, there's a discrepancy between the ranks. So one rank is actually allocating more memory than this bottom rank here. And in the middle would be this dark line. So this may be of concern to you if you are not expecting this. Like I said, you don't really know just how your code is behaving until you run it under a profile. And again, just like DDT was to invoke to launch a program with DDT, it's simple. It's just as easy to launch it with map, where you just stick map -- profile in front of your launching line. Okay. So DDT specifically, it's useful to help answer questions, about really what's going on. Try to figure out whether it affects all the MPI ranks or only affects a select few. Are all of the arrays having bad data, or is just a couple? Or is it only affecting the boundary conditions? So it's a tool to help you figure out and pinpoint, where the problems are. In this slide, what we have is we have DDT running on a pre-production MPI library code. And what was supposed to happen was that my PE was supposed to correspond to my rank. And if you've ever run an MPI code, you know that my rank is supposed to go from 0 to my rank -1. And you would see that visually in a diagonal line. Excuse me. Where 0 would be at the leftmost value, and then my rank -1 would be here, and you would expect a line. But just at a glance, they can see that this variable is incorrect. So they were able to fix it before this code actually made it into production. So this illustration, this graphical illustration, which is done on the fly on your code, is called spark lines. So in addition to the graphical representation across all the ranks, you get the new numerical representation for the rank that's currently in focus. And just like in the previous slide, where if you were to switch over to a different rank, this would highlight, or this would automatically update as you move between the ranks. Okay. Okay, so that's all fairly good and well. Just things, if you have a code and you want to run it with our debugger DDT, you really do want to enable the debug flags, add the debug symbols into your code by compiling with -G. And we also recommend that you turn off optimizations. If you think there could be a problem, you definitely want to turn off optimization flags. Because if you leave it on, the compiler has a tendency to optimize out some variables, and it may be the variable that you're actually looking for to help you figure out what's wrong with your code. So this is just pretty standard advice if you're to use a debugger of any sort. Okay, one of the most typical problems that you would use a debugger for is trying to figure out what caused a segmentation fault. So segmentation fault is like you probably touched memory that you shouldn't have, and then at which point the program refuses to continue further. So you can see this is what happens if you run it outside of DDT. You just have an exit on signal 11 due to a segmentation fault, and that doesn't tell you a whole lot. But when you run it under DDT, not only does it tell you that you're about to get a segmentation fault, it tells you where in your code that the fault occurred, and you can immediately see based on the here we're looking at the current line. We can see what the values are for the variables that are in scope. And it tells you you can continue to run the program, but it will probably be terminated if you try to continue because you've got some bad data. So in which case you would just pause at this point. So the program hasn't actually crashed; it's about to crash. Well, I mean, okay, it's about to crash, but you can still inspect the current status of things. So for this example, as you hit pause, like I said, you can just move your mouse over tab, because this is the current line that we're looking at, 103. This is where the crash occurred. And if you moved your mouse over tab and you hovered it over it, you can see that DDT is telling you that tab is an integer array, and it's got it goes from range from 0 to 12. And we're trying to access element X and Y, where X is a really large number and Y is a value of 0. And here you can see that because X is a really large number, it's clearly outside of the bounds, right? And that's the reason for this crash. I know this is like a really trivial example, but oftentimes a lot of the errors that you might see are trivial things that you weren't expecting. Because I know a lot of people think when they write their code, they assume that everything is correct as soon as they hit compile and run. But experience usually tells you that that's not always the case. Okay, so that was for a straightforward segmentation fault crash. You know there's a problem. DDT is also helpful for when there's code that works sometimes, but not all the time. And if you have a problem like this, more than likely it's some type of memory bug. And what you can do is that you can run it under DDT with our memory debugging libraries, and you can force the crash to happen. So when you're running a code, you just tick our memory debugging box, and there are different settings that you can change for heap debugging: fast, balanced, thorough, and custom. As you go from left to right, you incur more and more checks on the code itself. But there is a performance penalty, right? Because there's penalty in terms of bookkeeping, because we're keeping track of more information, and there's a performance penalty in terms of speed, because we're having to sift through a lot of information and keeping track of what's being allocated where. So we typically recommend that you actually start with balanced to help spot your memory issues. Oftentimes that's more than enough to figure out what's wrong. If that doesn't work, you can always go to thorough, but just be aware that if your code is already pushing the limits of how much memory it's consuming, you might want to drop it down and run it on more nodes so that you have enough, so that you have more memory available per node. I mean per MPI rank. Okay, so in particular, the fast, balanced, thorough, and custom. So the three different things here. As you move from left to right, you turn on more and more of these checks. So essentially what we're doing is we're painting the regions of memory as soon as you allocate it with your standard allocation functions, whether it's C or Fortran. And we're running additional checks. You know, one of the checks is we'll like Alec blank, it will put a known value for the initialization. And if that value ever changes when you were not expecting it to change, then DDT will prompt you and show you, hey, something happened behind the scenes, and you can try and figure out why that changes or why that changed. So in addition to those checks, we have what's called guard pages. It's traditionally known as electric fences, but what that is that when you allocate memory, you can put a safety net on either side, whether it's before or after the allocation. And what that does is that prevents you, if you were to accidentally touch this area outside of the normal memory allocation, DDT will tell you, hey, you were not supposed to do that. This is typically more applicable if you have a C code and you're dealing with pointers, and you or somebody else was being careless in how they were working with the pointers, and they touched something that they shouldn't have. This creates protected regions, and it will alert you whenever something has gone wrong. Okay, so like I was saying before, you can put printf statements in your code, but we had a customer that was simulating blood flow through a heart, and they had this code, and it would only crash when they had over, I don't know, like 1,000 MPI ranks or more. It was a high number. Here we can see that it's running on 24,000. But the point being is that the problem they were experiencing never showed up at a lower number of MPI ranks. So what they did was they run it through DDT, and they got to a crash in this par-administer routine. And if you're not familiar with a stack backtrace, so what this is actually showing is that in their main code, the main code calls a function, this function calls a function, and so on and so forth. And they got it down to this XYZ part.c file at line 556, and this is where the crash occurred. And this is the actual line of code where we're just taking we're just doing a reassignment, right? We're taking a value from one array of all picks and putting it into another array of my picks. So at a glance, this doesn't look like it should be problematic at all. But it turns out when they were looking at the local variables that are in scope, the value is optimized out because they did not compile their code with -0. And the reason they want NT samples is because that's one of the variables that's being used to address the all picks array. So they had to go back, recompile the code with -0, and then run DDT again. I mean, there's just no way around it because they can't see the value. And when they did that, they can now see a value for NT samples. They can now see a value for NPEs and I, and all of them look fine. They're all positive numbers. So I times NT samples divided by NPEs. So each of these three variables all look fine. They're all nice, positive numbers. Now, what they did was they did an evaluation of I times NT samples. And they noticed, hey, some of these values are negative. And that's not something you would expect, right? You've got two positive numbers and you're just multiplying them together. But when they evaluated what that expression should be, so notice that this was not like part of the code. This was an expression that they computed on the fly. They just, in this evaluation window, they just right-clicked in this area, added an expression. They said, hey, DDT, tell me what is the value of these two variables multiplied together. And DDT not only did that for the current MPI rank, it did it for all the MPI ranks, and then they can see that there was a problem here. The reason for it is because they had an integer overflow. So they were able to solve that, just by using unsigned integers instead of regular integers. But you can see it's a type of int, right? And once they did that, their problems went away, and they were able to run their code like normal. But this is an instance, where sometimes you may not be able to spot the issue without having a tool like DDT to help you. Right. Okay. Okay. And then another feature of DDT is that we do have version control built in. So some people get confused by this slide, and what I'm really trying to say is that if you check out a code and you know that it worked before, and then you check out a later version of a code, and then all of a sudden it doesn't break, chances are this new bug came from the latest change. And so you would want to look to see by date, which of the lines of code were recently changed, and then most likely, that's going to be the problem. All right, because from a fact, from experience, that it worked before. So that's one of the handy features of having version control, is you can go back and see what's changed. Okay. So as you're going through and debugging the code in DDT, every single action that you take, whether it's like setting a breakpoint, adding a trace point, it's all stored in this logbook. And you can also, if you click on the pencil, you can add notes to yourself, and then save this as an HTML file for you to come back to at a later date. So as programmers, when we debug code, we like to think that we can find the problem, solve it in a matter of hours. But sometimes it's just not the case, where it takes you more time than you're comfortable admitting, and you have to come back another day, or you need to make dinner, or you're running out of time, or it's time to go to bed. So you just have to stop. But you don't want to lose all the information or you don't want to. You want to remember everything that you tried previously, so you can track all your changes in this logbook, save it, and then make sure that next time you come back, you can either open it up and look and see what you did previously, or you can see what you did previously and then try something new this next time around. Okay. Do I have any questions so far before I move on to a live demo?
So we have one question from Chris in the Zoom chat. Can you see that?
Okay. Will DDT also break on other forms of error like Fortran bounce checking, which cause an abnormal exit, but not a segmentation fault? I think so, but I don't know for a fact. Sorry, I'm not a big Fortran user, but I'm fairly certain that it would. Okay. So at this point, I'll switch gears into my virtual machine. So I like having a remote Linux client. It's often easier when you're using our tools to download a remote client. If we have it for Windows, Mac, and Linux. That way, any graphical information that's going from my local machine to like Theta or any other machine that you're connecting it to, it becomes a real smooth experience. So in terms of configuring this, I've already got it configured for Theta. I'll just show you what it says. It's just my username at Theta and then the location of Theta. I have this in the slides, so you can look at that later for reference. But I'm just going to go ahead and connect to it. Okay, and then I got to put in my handy dandy passcode. So it's kind of like a two-step process. One, you want to connect your local machine, your local client to the compute node. So you can see I'm connected to Theta. And then I'm actually on the Theta machine and oh no, I lost my timeout. All right. I was connected. I'm gonna have to reconnect. Sorry, it'll take just a second here. I'm noticing my connections have been timing out. I don't know if that's my internet or something with Theta, but okay. Oops. Oh, debug and demonstration. Okay, so here I have a simple code. I'm just going to compile it. You'll notice I do something a little strange. I do recommend -G00. We've already talked about that. I'm also enabling memory debugging by doing this special link line. Again, this is also in the PowerPoint slides. The reason I do that is because by default, Theta makes static executables, and then if you want to use memory debugging, you have to link in it. You have to link our debugging libraries manually, which is no problem. Okay, and then I'm just gonna qsub this submission script. So, but you can see on screen, what all it's doing. It's just loading the Forge module, and it's doing DDT-S connect, and then running AP run on the executable. Okay. Hopefully this will start fairly quickly. Now, there's no bug in this code, but I'm running this as a demonstration to show you the features of DDT and just how really easy it is to navigate between your code and explore all the features that DDT allows. Okay. I hope it's going. That's starting. So I will make I will make this code and others available later for the hands-on. But for now, just follow along. So as soon as it ran, because there's this DDT-connect command in the script, and I was already connected with my local client, so I now have the reverse connect request, and I just got to accept it. So saying yes, I do want to debug this code.
Ryan, we have 5 minutes now.
We have 5 minutes.
5 minutes.
Oh,
yes,
okay. Wow. All right. Sorry. Okay. Well, I will make this quick then.
course, you can carry on in the breakout later too.
In the breakout. Okay, yeah, sure. Wow. Okay, yeah, so I'll just carry on with, okay. I'll continue this in the breakout session. Sorry about that. Okay, let me just continue with the slides here just so I can talk about map. We also have GPU debugging. At the moment, it's just NVIDIA cards, but we are planning on supporting AMD cards. And we'll, in the future, we'll hope to support the Intel GPU or accelerators, excuse me. By default, we work with CUDA for NVIDIA, but we can do OpenACC CUDA kernels. We cannot do OpenMP offload at the moment. We do offer Python debugging, where it's, in this case, this is actually mixed Python with C, where Python is actually calling C code to do a matrix multiplication. And we can work natively with NumPy arrays or NumPy data types and NumPy arrays as well. Okay, and then here is just commands to go through DDT. On the other side, we have our profiler map. Some map is here to tell you where time is being spent line by line. The idea is to identify the hotspots. You don't have to modify your code. We do recommend that you compile with -G just so that you can see the source line, but it's not necessary if you're only interested in the time spent in functions. At a glance, you can see how memory is using. You can see the MPI communication patterns. If you have a sawtooth pattern, that typically means that one MPI rank is waiting for communication from another MPI rank before it can move on. You can see how the CPU is being accessed. So here we've got a lot of memory accesses here, and then in addition, we've got the high vectorization usage in that region as well. I'll just skip through this. Here, this is something that was there were I/O issues. So they were able to see that the data transfer rate only goes from 0 to 14 megabytes per second. So clearly there was something wrong. They were able to change out the code, use more efficient library calls, and now the disk write transfer goes from 0 to 75.3 megabytes per second. And then actually it really improved the runtime of the code. And in addition to debugging Python, you can also profile Python. Here we can just see that if you use like naive Python without using any NumPy performance libraries, you're going to spend a lot of time in the Python interpreter, which is not very fast. And as soon as you move to a NumPy loop, you get much better performance. Here we're solving the same problem with 10 times more iterations, and it's even taking less time. It just helps you identify, where time is being spent in Python code as well. Okay, and on Theta, like I said, I can go over this in the hands-on. This is how you would set up your remote client. Theta GPU is a little bit different because you have to go from the Theta login node to the Theta GPUs node before connecting. And I can cover that in the hands-on section as well. Like I said, if you wanted to statically link, you would do this. And on Theta GPU, apparently, you will have to use this temporary license if you're wanting to use Theta GPU, mainly because Argonne doesn't currently have a CUDA license. So if you want the CUDA features, you have to use this trial license. But it's good for the next week. So you're able to test out your codes there. And also, as I said in Slack, if you have access to an AWS instance, that runs on ARM hardware, you can also take this file and copy it over there and run our tools on ARM hardware if you'd like, on an AWS instance. In profiling on Theta, if you see this, if you see these issues, this is what you would do. And all of the hands-on stuff will be available in this directory. Okay, so yeah, that's time. Any questions?
Yeah, thank you, Ryan. It's on time. I think we have one question from Chris. Can you quickly answer the question? While the Nikolai share the screen?
Sure. Where's the question?
In the Zoom chat. Yeah.
Is there how to use DDT to debug a program that must be run through a series of scripts that first set up the running environment? No, you just have to be familiar with the script itself, figure out where the actual launch command is, and then be able to insert DDT in front of whether it's MPI run or AP run or something like that. And unfortunately, if you have a complicated script, you're going to have to figure out where to insert that yourself.
Okay, so yeah, since we don't have enough time, so we have another question from Angel. But Angel, please leave the question in the Arm Slack channel so we can continue to discuss at the hands-on. And I think I can see the Nicolay's presentation. Can you change to presentation mode, Nicolay?
Yes.